Hi everyone, this is the first of 2 videos on economical coding. To motivate the material that follows, we begin with an introductory discussion. So what I'd like you to do is to pause the video now and look at the setup here on this slide and questions A, B, C, and D, and think about them for a little bit. Maybe even make a few calculations and then come back and we'll talk about it a little bit. Okay, at this point, I'm assuming that you have paused the video and thought about some of these questions. So the first question, part A, is whether the code that we've been given is uniquely decodable. So here's our code, and how would we know whether it's uniquely decodable? Well, if you look at the code, you can see that it's a prefix-free code, right? No code word begins with another code word. And we saw in the last video or so that any prefix-free code is automatically uniquely decodable. So the answer is yes. Here, it is uniquely decodable because it's prefix-free. All right, now our alphabet, S, has 5 objects, and our code has 5 objects. And if we're going to, use the code C for alphabet S, then we need to assign the elements of S to the code words that are in C. So here in part B, we're going to assume that if we form messages out of alphabet S, that the letter V will occur with probability 0.28. The letters W and X will occur with probability 0.22 each. And then the letters Y and Z will occur with probabilities 0.14 and 0.14 each. So the letter V is the highest probability letter, meaning it occurs the most often, whereas Y and Z are the lowest probability letters. So on average, they are going to occur the least often. So the question is, how should we assign these symbols to the code words in C so that the length of a coded message is likely to be minimal? So since this letter V occurs most often, we would want to assign V to a pretty short code word, right? We don't want to assign V to 010 because then that most commonly occurring letter is going to get a code word of length 3 rather than some shorter length, right? So it makes sense that we would assign the highest probability letters in S to the shortest code words over in C. So maybe, I don't know how you all did this, but maybe it would be a good idea to assign V to 00, and then W and X have probabilities 0.22 each. So those are the next in line. So maybe W and X are assigned to 10 and 11 respectively. And then the least commonly occurring code words, Y and Z, they can be assigned to the code words of length 3, namely 010 and 011. Okay. So that seems like a reasonable assignment of letters in S to code words in a way that's going to minimize the average length of messages. Now, what you might think is you might just stop and say, well, wait a minute. If these are the probabilities with which these letters in S occur, then maybe what we should do is throw this code C out the window and start with an entirely different code that will make the average length of coded messages even shorter. So let's suppose we do exactly that. Let's throw code C out the window, and instead, let's consider this code C tilde. Now, C tilde also is a uniquely decodable code. It's a prefix-free code. It's got 5 code words in it, so we could use code C tilde to encode all of the elements of the letters in S. And then the question is, how would we assign these letters? Well, again, the most commonly occurring letter, which is V, appearing with probability 0.28, would be assigned the shortest code word. And then, the next commonly occurring one is 0.22, so that's W. And then in order, the next is X, so we assign X there. And then Y and Z are the least commonly occurring, and so they should be assigned to the longest code words. Now, if we do that, that's the best assignment of alphabet S to code C tilde. But does it gain us anything over using this original code C? That is, would the length of a message on average be shorter in C tilde, or would it be shorter in C? So that's something, perhaps you did some calculations on that, and we'll talk about that a little bit more later. All right, now the computations that you did in parts B and C, they might be affected by the probabilities with which the letters in S occur. So let's suppose we changed our list of probabilities to something like this, right? Let's suppose that V occurs with probability 0.67, W with probability 0.20, X with probability 0.10, and Y and Z both occur with probabilities 0.015. That might change whether we decide to use C tilde or C in order to, minimize sort of on average the length of a message. So we didn't come to any conclusions in the discussion on the previous slide. No firm conclusions at any rate. We just brought some ideas to the forefront that we're going to want to discuss in some more detail as we proceed. So we attempt to make sense of the previous discussion by studying what are called optimal codes. Okay, so under certain conditions, these codes, namely the optimal codes, are going to minimize the length of a coded message on average. To talk more about optimal codes, we need some terminology. So the first piece of terminology is the notion of a source. So a source is an alphabet, S, consisting of some letters, together with a probability distribution. And these two are joined in the following sense. So if we have a stream of symbols from S, then the probability that symbol S sub I occurs in any given location, X sub K, is probability Pi. So S sub I, the letter S sub I, occurs with probability P sub I in any given location. So further, we say that the source is memoryless if, when you look at two particular locations within the stream, if you want to know that the probability that S sub I lies in the first location and S sub J lies in the second location, then we can get that probability by just simply multiplying the two individual probabilities, p sub I and p sub j, together. So in the language of probability, what we're saying is that these variables, x sub k and x sub l, are independent random variables. That means that probability of, an alphabet letter occurring in position x sub l is not conditioned upon what occurs in x sub k. All right, so a little example on these. So we're going to consider a memoryless source, S comma P, where S is just this three-letter alphabet, A, B, C, and P is the probability distribution, 0.6, 0.3, 0.1. So again, what this means is that letter A occurs in a stream of symbols at any given location with probability 0.6. B occurs with probability 0.3 at any given location, and C occurs with probability 0.1. So one thing you might remember about probability distributions, at least discrete probability distributions, is that all of the probabilities must add up to 1. And so the first thing for us is to check that this is true for our probability distribution. And indeed it is, right? Because 0.6 plus 0.3 plus 0.1 does equal 1. Okay, now in item 2 of part A, let's suppose this source emits a stream of 100 symbols. So the question is, first question anyway, is approximately how many times will the letter A occur? Well, each letter A occurs with probability 0.6 in any given location. Now, there are 100 locations in this stream of symbols, so the number of times that A would occur would be 100 times 0.6, which would be 60. So that's how many times we could expect the letter A to occur in a stream of 100 symbols. So the second question is about consecutive pairs. So how many times will the consecutive pair AB occur in a stream of 100 symbols? So if you think about 100 symbols next to each other, there are 99 consecutive pairs. So there's the first and the second and the third, and so on and so forth up until the 99th and the 100th. So there are 99 consecutive symbols, or consecutive locations in a stream of 100 symbols. And then what's the probability that the pair AB occurs in each one of those consecutive pairs of locations? Well, remember, A occurs with probability 0.6. B occurs with probability 0.3, and the source is memoryless. And so that means that if I want the probability of AB occurring in a consecutive pair, it's just the product of the two probabilities. So 0.6 times 0.3 would be 0.18. And so that, if you take 99 times 0.18, whatever that number is, that's about how many times we would expect A times B, or not A times B, but the pair AB to occur in this list of 100 symbols. All right, now part B of the question is to consider a stream of symbols in the ordinary English alphabet. So here we're throwing the alphabet, this sort of abstract alphabet, over our shoulder, and we're replacing it with the ordinary English alphabet, A through Z, and we're considering English words in the English alphabet. Is that a memoryless source? That is, do relative locations of symbols affect what might or might not be there? And I think if you think about it for a little bit, you'll see that the answer is no, right? For instance, if you look at the letters Q and U, right? Q and U, they each have a certain, they each occur in English sentences with a certain probability. But, you know, if we're, say, looking at consecutive symbols and the first symbol is a U, or excuse me, the first symbol is a Q, then it is highly likely that the very next symbol is a U. In fact, it's going to be much more likely that that next symbol is a U than the probability that U occurs, say, in any other sort of setting. So English is not memoryless. Now that we've introduced a source, we can introduce the idea of average code word length. So we start with a source, S, P, which you recall consists of this alphabet S, together with a probability distribution P that tells us the probability of a given letter occurring in a given location. So to this mix, we're going to add a code now. So this code is going to take letters in S to strings on this alphabet T. And we're going to let Y sub I denote the length of the code word that's associated to the letter S sub I. So let's suppose we start with a message of length capital N in S star. So this is more than just a single letter in S. It's a combination of letters occurring in S star. And let's suppose we have that message and we want to encode it. Well, we know that to encode that message, we encode each letter individually. So we do that n times for each of the n letters that are in the original message. And what we want to know is, well, on average, so when we say approximately, what we really mean is on average, how long is the resulting coded message? So that's a number that's going to be important to us because remember, we're trying to make these coded messages short as we can. So anyway, the expected or average length of the encoded message is going to be this sum. All right, so why should that be the case? Well, let's look at the very first term of this sum. So this object, n times p1, that is the average or expected number of times that the letter S sub 1 appears in our message of length capital N. Right, so that is the expected number of times that S sub 1 appears in our original message of length capital N. And then when we multiply by Y1, remember, Y1 is the length of the code word associated to S1. So that's going to give us the total length of the coded message that is due to the code word C of S1. So we just keep doing that, right? In the second term, N times P2 is the expected number of S2s in the message, and then we multiply by the length of the code word that is associated to S2, and that gives another contribution to the length of the coded message. So we do that for all of, up until we get through the end of the alphabet, right? We first consider S1, then we consider S2, and then we compute the expected number of S sub m's in this message here again of length capital N. And then when we multiply by Y sub m, which is the length of the code word associated to S sub m, we get a contribution to the length of the coded message. All right, so this expression gives us on average the length of the coded message. Now we can factor the capital N out in front. Remember, capital N is the length of the original message. So if we factor that out in front, what we have is this expression, P1 times Y1 plus P2 times Y2 up through PM times YM. And that, the natural interpretation of that remaining sum, which we're going to refer to as L, is as the average length of a given code word in this message. Right, so this again, this L, which is this sum inside the parentheses, is called the average code word length. Now, it makes sense that encoded messages are going to be shorter on average when L is smaller. Therefore, we have a goal that we'd like to meet. So given a source, S, P, and an alphabet T, we'd like to be able to find a uniquely decodable code from S to T star for which this average code word length is as small as possible. So if we meet that goal, we will have promoted our sort of larger or meta goal of economy in coding, right? We'll have made our messages on average as short as they can be. Now we compute some average code word lengths. In this setting, we have our alphabet S consisting of letters V, W, X, Y, and Z. We also have a couple of probability distributions and a couple of codes. So if you look over this setting, it looks familiar probably to you, and it should, because this is the exact setting that we had in our introductory exercise at the beginning of this video. And as we go forth and make some computations here, I think it will be interesting to see whether any of those computations are reminiscent of calculations that you made during the introductory task. All right, so the first thing we're going to do is compute the average code word length for the source S, P with code capital C. So before we dive into making that calculation, let's just make sure we understand the setting. So our alphabet S is, again, these letters V, W, X, Y, and Z. Here we're looking at the source where the probability distribution is P. And so that means that the letter V occurs with probability 0.28 in any given location in a stream of symbols. W occurs with probability 0.22. X occurs with probability 0.22, and Y and Z each occur with probability 0.14. Now, we're using code capital C, and we should always assign shorter code words to letters that have higher probabilities. So that means that we would assign, in this instance, or would make sense to assign V to 0, 0, W to 1, 0, X to 1, 1, and then Y and Z to the longer code words 0, 1, 0, and 0, 1, 1. Okay, so let's go ahead and compute average code word length now. So in this setting, so the probability of the first code word, the probability of the first letter in our alphabet occurring in a given location is 0.28, and the length of its corresponding code word is 2. So that's the first term in our sum. And then the next letter occurs with probability 0.22, and its code word also has length 2. Next letter, again, probability 0.22, and its code word has length 2. And then for the remaining code words, their lengths are of length 3. So probability 0.14, length of the code word associated to Y would be 3. And then finally, we have 0.14 times 3. So now we add all that together, and when you do that, you should get 2.28 as the average length of a code word in a coded message here. Okay, now in the introductory task, we asked the question, well, let's suppose we have the same alphabet and the same probabilities, but instead of using the original code capital C, let's suppose we throw it over our shoulder and use a different code, C tilde, right? So let's compute the average code word length here and see how it compares to the original. So if we do that, here now the probability of V occurring in a message is 0.67. I'm sorry, this is wrong. Right? So here again, the probability of V occurring in our message is 0.28. But now the length of the code word that we associate to V is 1. And then we have 0.22, which is the probability of W occurring. And then the length of W's code word is 2. And then keeping on, the length of the next code word is 3. And then the lengths of the last two code words are 4. And if we add all that stuff up together, we get 2.50. So if we have source S comma P, and we're trying to decide between codes C and C tilde for economical coding, we would choose code C, right? Because its average code word length is smaller than the average code word length for C tilde. All right, now we'll do exactly the same thing again, except now instead of having these letters of our alphabet occur with probabilities given in distribution P, we're now going to look at distribution Q. So this says V occurs with probability 0.67, W occurs with probability 0.2, X occurs with probability 0.1, and Y and Z each occur with probability 0.015. So let's go ahead now and compute average code word length. So now in part C, we're going to use our new source with probability distribution Q and our original code, capital C. So our first probability in this new setting is 0.67. The length of the first code word in C is 2. And then we have 0.2 times 2 plus 0.1 times 2 plus 0.015 times 3. So we're now on to the code words here of length 3. And again, 0.015 times 3. And if you add all that stuff up, you should get 2.03, or at least that's what I got. It's 2.03. Okay, so we have done code C, and now let's do code C tilde. So by now you're probably getting the point about how to do this. So it's 0.67 times the length of the first or shortest code word in C tilde, which would be 1, plus 0.2 times the length of the next code word is 2, 0.1 times 3. And then we have these very small probability code words, each of length 4. And now if you make that sum, I get 1.49. So again, now let's suppose we have source S comma Q, and we're trying to decide whether to use code C or code C tilde. And we see that C tilde has the smaller average code word length, and so that would be the one that we would choose in that setting. So the discussion that we've had over the last couple of slides leads to a natural question, and that is, if I have a source, how do I choose a code that will make my average code word length small? So we're going to need to address that question, and in order to do that, we need a reformulation of this Kraft-Macmillan number that was introduced a few videos ago. So remember that, if we have a code where the size of the code alphabet is B, that the Kraft-Macmillan number is n sub 1 over B plus n sub 2 over B squared up through n sub m over B to the m, where remember that n sub j is the number of code words of length j, right, where capital N is the maximum length of a code word. So this formulation should look familiar to you of the Kraft-Macmillan number. And we showed, remember, that that number is less than or equal to 1 if and only if there exists a uniquely decodable code with the parameters n1 through n sub m. Now, it turns out that we can also write the Kraft-Macmillan number in this way. So B, remember, is the size of the code alphabet. Y1, Y2, what are those? Well, remember from the previous slide, we're going to let Y sub j denote the length of code word S sub j. All right, now it may not be apparently or immediately obvious why these two expressions are the same, and you might ponder that for a little bit. For the moment, we're just going to just flat out compute Kraft-Macmillan number using both of these methods just to see that we get the same answer, all right? So let's look first at code capital C. So in this case, B is equal to 2, right? These are binary codes. And first of all, how many code words are there of length 1? Well, I go through C and there are no code words of length 1, so it's 0 over 2. Now I'm looking for code words of length 2. I see there are 3 of them. 3 code words of length 2 over 2 squared, which is 4. And then there are 2 code words of length 3 over 2 cubed, which is 8. And then there are no code words of length 4 or 5 or any other thing. And so this is the end of my Kraft-Macmillan sum. That turns out to be equal to 3/4 plus 1/4 is 1. Now let's do the same code again. So this is code C, looking at code C. But now we're going to use this second formulation. All right, so first I take 1 over B. So B in this case is 2. And I look at the length of the first code word. So the first code word is of length 2. Then I go to 1 over B to the length of the second code word. Well, the second code word also has length 2, as does the third code word. And then we go on to the fourth code word. So I'm looking at now y sub 4 as the exponent. Remember, y sub 4 is going to be the length of the fourth code word, which is 3. And again, The fifth code word has length 3. And so this will also be our Kraft-Macmillan number. And you might see that this portion of the sum corresponds to the 3/4 there. And that portion of the sum corresponds to the 2/8 there. And we wind up with exactly the same thing. So anyway, I think you get the point here about how to make these computations. So I'm not going to do the one for C tilde. Now we're ready yet again to refine the goal. So remember, our original goal was a little bit hazy, right? As under certain conditions, we want to find a uniquely decodable code that minimizes the length of a coded message on average. So now our refined goal is as follows. If we're given a source, S comma P, and an alphabet T, we want to find a code, capital C, from the alphabet S to strings T star, such that the following things happen. First, we want this L to be minimal, subject to the Kraft-Macmillan number being less than or equal to 1. So remember that B here is the size of the code alphabet T. All right, so this sort of unrefined goal about minimizing length of coded messages now becomes a more mathematically precise goal where we want to find a code that minimizes L subject to constraint given by K. Right, so items 1 and 2 here, item 1 minimizes the average code word length, right? Remember, L is the average code word length, which in minimizing that, we will on average minimize the length of coded messages. While item 2, this constraint is imposed so that whatever code we choose is uniquely decodable. Right? Remember, whenever the Kraft-Macmillan number is less than or equal to 1, then we can choose a code, a uniquely decodable code that has the given parameters.